Hassler here. I'm going to do the lesson for 8.5, but before we do that, I just want to do a couple introduction problems so that you can understand why we end up doing what we do during lesson 5. And so problem 1 says, in a geometric sequence, the first term, f of 1, is equal to 8, and the third term, f of 3, is equal to 200. Which number represents the common ratio of a geometric sequence? And so if I were to create a table or a list of numbers, the first number in my list would be 8, and the third number in my list would be 200. And I have to figure out, what can I multiply 8 by? Twice times r, and then multiply that number times the same r to get to 200. And this is a multiple choice. It gives me some options, and so I could try those options. If I do 8 times 5, I get 40, and 40 times 5 is 200, so it turns out to be 5. And so because of my choices, I can reason through that. So let's try another one. It says, in a geometric sequence, the first term is equal to 3, and the third term is equal to 48. Which number represents the common ratio? So again, I'm thinking, okay, my first number is 3, and my third number is 48. And again, I'm going to have to multiply 3 by some number, r, and then multiply that answer by the same number, r, to get to 48. And so this one is a little bit more difficult because I don't have these choices. So I'm going to think about it like this. What's it going to take to get from 3 to 48? Well, let's see. 48 divided by 3 is 16. So it'd take me 16 to get from 3 to 48. I really, though, have to move 2 spots. And so that means, what if I times 4? 3 times 4 is 12, and 12 times 4 is 48. So it turns out that ratio between the two terms is helpful to know, because I have to skip a term to go from 3 to 48, and I can think of 16 as 4 times 4. And that helps me get from the first term to the second term, and the second term to the third term. Let's see if that works here in problem 3. So problem 3, it says, my first term, in a geometric sequence, my first term is 64, and my third term is 16. So again, I got 64, and then I have 16. And again, I have to multiply by r, the same number each time, to get from 64 to 16. And so I'm going to go ahead and figure out, okay, 16 divided by 64. If I do 16 divided by 64, I'm going to get 1/4, which is really 0.25. And so to get from here to here, I have to multiply by 1/4, or 0.25. And so I have to think about, what is it going to take to go from here to here, from the first term to the second term, and the second term to the third term. And let's see. What if I do by half? What if I do half? Half of 64 is 32, and half of 32 is 16. That works. And it turns out that half times half gives me 0.25. It turns out that what we're dealing with here are perfect squares. Up here at the top, if I did the square root of 16, square root of 16 is 4. And if I did the square root of 0.25, the square root of 0.25 is 0.5. And if I come back up here, and I try this, similar story, I say, okay, what would it take to get from 8 to 200? Well, let's see, 200 divided by 8 is 25. And so if I do the square root of 25, I would get 5. And that's ended up what it was, multiplying by 5. And so that's what we're going to work on today, this idea that I'm going to start at 8. I have to multiply by 2 r's, or r twice, in order to get to 200. I can divide both sides by 8 and say, okay, r times r, that's r squared, is 25. And so I can take the square root to figure out what r should be. And that's going to take us into our lesson today. All right, so let's transition over to our lesson. And our lesson says, we are exploring how much acetaminophen is left. And acetaminophen is just Tylenol. So acetaminophen is a pain-relieving drug found in medications like Tylenol. Acetaminophen enters the bloodstream and over time is absorbed by the tissues. A patient receives 400 milligram dose of acetaminophen, and after 2 hours, 256 milligrams of the drug remains in that bloodstream. So I'm going to complete the table with the information provided above. So I know that initially I received 400 milligrams, and after 2 hours, I have 256 milligrams. Okay, that's all I know. So that's all I can fill out in my table. It says, assume the acetaminophen is absorbed by the body at a constant rate. And when I see the words constant rate, I'm thinking, okay, linear function, which means I'm adding or subtracting the same number each time. Okay. So how many milligrams are absorbed per hour if I'm looking for a constant rate? That means I'm looking to go from here to here and here to here. My numbers are getting smaller, so I have to subtract by the same number each time. So to figure this out, I got to find the difference between the two. And because I'm skipping 2 spots, I'm going to divide that answer by 2. When I do that, I get negative 72. Negative because my body is absorbing it. So I'm absorbing, or I'm taking in 72 milligrams. It says write a linear function f of t to show how many milligrams of acetaminophen remains. Okay, so that means I'm going to start with f of t equals, I need my initial, so this is going to be my f of 0, and f of 0 is 400, that's how much I started with, okay, minus, and then I need how much I am absorbing, right? I'm taking 72 away, so 400 minus 72 tells me how much is left. So this is going to be that common difference, that number I'm adding or subtracting by. In this case, I'm subtracting 72 each hour, so I need a big T. Not exponential, so there's no exponent here. All right, so let's keep going. This would be if it were linear. In reality, acetaminophen is not absorbed at a constant rate. Instead, a certain percent of the acetaminophen is absorbed. How is this different? Well, now we're looking at an exponential function. We're looking at exponential because percent means that we're going to multiply our amount by whatever that percent is, okay? So now we're going to have exponential. I'm not subtracting each time. Now I'm going to multiply by a percent. While it's helpful to think about the percent of the drug that is absorbed, it is more common for medical professionals to think about the quantity that remains in the bloodstream. So what proportion of the initial amount, what proportion? Proportion means I'm looking at a ratio. Okay, what proportion of the initial amount remains in the bloodstream after 2 hours? So after 2 hours, I have 256 out of 400. So out of my initial amount, I had 256, which is 0.64. So that's my proportion. If I'm thinking about this as a percent, that was 64%, but that was over 2 hours. I want to know now what proportion of the drug remains in the bloodstream each hour, okay? And so this is what I was talking about earlier, this idea that we started with 400, we're multiplying by R twice to get to 2 hours later. So zeroth term, to get me to the first term I multiply by R, to get me to the second term I multiply by R. That second term is 256. I'm going to go ahead and divide both sides by 400. We already did that. We did that over here, okay? And R times R is R squared. So I have R squared equals 0.64. And so I'm going to take the square root to get rid of that square. So R is equal to 0.8. And now I can use this to finish my table up above. So what that means is I'm going to take this 400, I'm going to multiply it by 0.8 to get my new answer. When I do that, I'm going to end up with 320. And so I multiplied that by 0.8. I'm going to multiply that by 0.8. I get 256. I'm going to multiply that by 0.8. I get 204.8, but we'll say 205. And I multiply that by 0.8, and I'm going to get 164. And I multiply that by 0.8, and I'm going to get 131. Okay? And so I have this geometric sequence. It says what percent of the acetaminophen remains each hour, and so what percent is absorbed. Okay, so I'm going to label remains and absorbed. Okay, so remains is what I found as this 0.8. 0.8 remains. And so if 0.8 remains, that means that I have 80%. And so if I have 80% remaining, then 100% minus 80% is 20% absorbed. And so now I'm going to write an exponential function to show how many milligrams remain after t hours. All right, so R of t equals, all right, I need my initial, that's f of 0, and that's the 400, times, I need my R value for remains, and we do this as a decimal. And so we've got the remaining decimal is 0.8 to the t. Because it's exponential, I have a t as an exponent. Okay, so a couple things we're hitting in this lesson. One, we're talking about arithmetic or linear versus geometric or exponential. And we're talking about finding a common ratio when I have non-consecutive terms or when I skip terms. So let's go ahead and move on to those quick notes.